All right, it's noon time. So again, next test is next week, Wednesday. And Oscar, you don't have to come for that. You don't have to come for the review either if you don't want to. But review's on Monday. And test on Wednesday. And I bought a bag of Halloween chocolate candies, so... And I'm slowly eating it myself.
No.
It's kind of hard not to eat those. So if you want to come to office hours, you can also have candy. As my students in lab were teasing me. So I'm also really excited because this is also when turkeys are on sale at Foodland. And I'm already eating one. I got one. I cooked it last night. So it's gonna feed me well all for a couple days. Anyways, so like I said, this stuff is not on the test. But does anybody have any questions about anything? It can also be about the previous materials, it can be about the test itself. No questions? Alrighty then. So we're at chapter 9. And chapter 9 is all about bonding. So now we're going to go into bonding. And there are 3 types of bonding. There is ionic bonding, where you have one element will give its electrons to the other elements. And for instance, sodium chloride table salt is an ionic bond. The sodium metal gives an electron to the chlorine nonmetal to become chloride. And then, if you can see, it's kind of a shadowy picture. I took it straight out of my textbook, but you have the green chloride anions and then the smaller purple sodium cations there. And they join together just by Coulombic attraction. So positives and negatives attract, positives and negative repel. So, and then there's metallic bonding. Metallic bonding is when you have, it's within a metal, and then there is a sea of electrons between the atoms is what causes the bonding. And I think I said this before, ionic bonding is the easiest of all the bonding to understand. Metallic is pretty easy. We understand most everything about metallic, and then covalent bonding, which is the sharing or sometimes unequal sharing of electrons. This is the one that's by far the most complicated. So we're going to spend the most time talking about covalent bonding. But we probably won't get to that today. But if I said you're in a group of 3, and if you have to cover all of bonding, pick ionic bonding as fast as you can. And if not ionic, pick metallic. And then the person that you don't like, stick him or her with covalent, because it's really the most difficult. Okay, so going back to sodium chloride, and I'm going to come up with this something we call the lattice energy. So this is what binds the lattice together. The lattice being the compound. So in this case, so if you look at sodium chloride here, the crystal structure gives its energy because of the attraction, the Coulombic attraction. I guess I should talk about Coulomb's law. I know I mentioned physics sometimes this class. This is Coulomb's law. The force is equal to some constant, in this case 1/4 pi over epsilon naught. Charge of Q is charge of 1 over charge of 2 over the distance squared between the 2 charges. So, and for positive and negative unlike charges, that's an attraction force. Like charges is a repelling force. And it's much the same thing with gravity. Gravity is the same formula, but it's mass of 1, mass of 2, and the constant is very different for gravity. It's much, much smaller for gravity. Anyways, let's go back to this lattice energy. And let me, I guess the screen won't help. So, remember I mentioned, please sit down. Remember I mentioned that thermodynamics is path independent. So it doesn't matter what path you take. So here we have sodium metal and chlorine gas making sodium chloride. And this is a potential energy diagram. So the y-axis is energy, x-axis doesn't matter. Y-axis is energy, this saying that sodium metal and chlorine gas is higher energy than sodium chloride solid. Actually, I can show you this reaction. I can do it with my, no, that's sodium, I'll do chlorine, I think. Yeah, here we go. So here's making sodium chloride. So that's sodium metal, and there's chlorine being piped in there. There's chlorine. And there is the formation of sodium chloride.
Everyone back.
And that guy is Theodore Gray. He's kind of nuts. Theodore Gray, and he wrote the PR table. Like, it's in the back of the class. Actually, no, that one's not Theodore Gray. The one in the lab is Theodore Gray's. But he wrote an e-book about the elements that's been popular for the past, I don't know, 5-10 years. Anyways, you can see, oh, where'd that go? And is it still recording? Okay, still recording. So students at home, don't worry, technical difficulties. All right. I don't know why it stopped doing that. There we go. All right. So the reaction of sodium and chlorine is exothermic. So you saw it caught on fire. And that's the thing about fire. Fire doesn't have to be with oxygen. You can burn things in other gases other than oxygen. Oxygen is by far the most common. But you can burn things in chlorine. So it's exothermic. But what we can do is we can take all of these, and it's path independent, so we can break up into steps. So what happens to sodium solid and chlorine gas? Well, we can take sodium solid and turn it into sodium vapor. Okay, so vapor. So whatever the opposite of heat of sublimation is. This will be the melting point plus the vaporization of sodium, and then chlorine can go from Cl2 to just plain old Cl, so that chlorine can rip apart into its atom, and then you can rip an electron off of sodium. So this is all endothermic. It takes energy, and then the electron affinity. So this, I'm not that tall. So you see here in this step here, sodium is being vaporized, chlorine is being ripped apart, and then we're ripping off an electron from sodium. And this step from here down to here, we are adding an electron of chlorine to form chloride gas. So we have sodium ion gas and chloride gas. And then the sodium chloride combine together, and we get sodium chloride solid. And this step here, from the vapor of sodium ion and chloride anion going to the solid, that step is what we call the lattice energy. That is this energy that's there. So, and although we've never directly measured it, we can calculate it. It's kind of a fictitious thermodynamic property in a way. Oh, and this is known as the Born-Haber cycle. So it's written on the top there. That's the Born-Haber cycle, and it's this fictitious lattice energy. And what I have here, this delta H, the delta H of reaction, this is the delta H of reaction right there. That's the going from here to here. That's the delta H. So here is our delta H. Delta H is this first step plus the second step. Here's the first step, second step, third step, fourth step, fifth step. So if you add those up together, you get the overall reaction. Or you can look at it this way, as that the number 5, or the lattice energy, equals delta H minus 1, minus 2, minus 3, minus 4. That way. So, okay. So let's talk about this lattice energy. How are we doing? Sorry, questions with anyone? Okay. So let's talk about the strengths of lattice energies. And there are two things that are going to affect the lattice energy. It's the charge and the size of the atom. So the Coulomb's law is constant. The force is equal to some constant times a charge of 1, charge a second, over the distance squared. So that means the bigger the charge, the stronger the attraction. Likewise, the smaller the charge, the weaker the attraction. Also, the smaller the distance, the greater the attraction, or the bigger the distance, the weaker the attraction. So, let's look at let's start with the distance. And you see here, so we're going to keep chlorides the same. So chloride's the same when you're changing the alkali metal. So sodium is smaller than, lithium is smaller than sodium, is smaller than potassium, is smaller than cesium. So as we go down the periodic table, they get bigger. And let's look at the magnitude of the lattice energy. So lithium chloride, with the smallest radius, has the highest lattice energy. And as they get bigger, the lattice energy decreases. So you see that? So the bigger the size, the weaker the lattice energy. Oh, and in case you're wondering, the ionic bond is pretty strong. So it's pretty hard to break an ionic bond. I mean, you think like, well, you dissolve salt in water. That's pretty easy to do. But the forces between the ions and the ionic bond is pretty strong, as evidenced by the fact it's really hard to melt them. So has anyone ever melted salt before? I never have. You can take salt and hit it with a blowtorch. It'll glow red. It'll glow orange. It won't melt. So it's really hard. You have to heat it up really, really high to melt salt, or any salt. Metals vary, and non-metals tend to have low melting points. But talk about that next semester. Oh, and I should also mention, today is the last day to drop any class. I know no one would ever dare drop chemistry, of course. But in case you need to drop another class other than chemistry, then today is your final day. Okay. So we mentioned size. So the bigger the size, the weaker the bond, or the smaller the size, the stronger the bond. What if we pick two things that are about the same size, but, or at least the distance between them is the same, versus their charge? So sodium fluoride that you find in toothpaste has an internuclear distance of about 231 picometers, and calcium oxide has an internuclear distance of 239 picometers. So a little bit bigger in the calcium oxide, but more or less about the same size. So let's go back to Coulomb's law. Charge of 1 times charge of second over the distance squared. Distance squared is about the same. So plus 1 times minus 1, that equals 1. Plus 2 minus 2, well, minus 1 I should say. Plus 2 minus 2, that's minus 4, right? So plus 1 minus 1 is 1, negative 1. Plus 2 minus 2, minus 4. So assuming that they're about the same size, we should expect that calcium oxide is 4 times as strong as far as lattice energy. And what do we see? So sodium fluoride, negative 910. calcium oxide, lattice energy, minus 3414. So 9 times 4 is 36. So it's about 4 times. Why is there a discrepancy? Well, it's also a little bigger, right? So this is 231, 239. So it has the 8 picometers. So that's why there's a little bit of a difference there. So, but do you see this here? So what does this tell us? Charge is more important than distance for ionic compounds. The strength of the lattice energy. And this also kind of makes sense, and let me relate this back to things dissolving. So remember we talked about solubility rules? If there's a relatively weak ionic bond, things will be able to dissolve in water. And if there's a stronger ionic bond, they won't dissolve in water. So which ones are the ones that are soluble? All the alkalis, ammoniums, nitrates, acetates, all +1, -1. And then the +2s, very few. The higher the charge, you get less and less likely to be soluble. The insoluble ones, things like the phosphates, the -3s, that's all insoluble, except for the ammonium and alkali, of course. So the higher the charge, stronger the lattice energy, stronger the ionic bond, less likely to be ripped apart by water. They all also have higher melting points. Okay, so let's use this logic. So arrange these ionic compounds in order of increasing magnitude of lattice energy. So low to high. So remember, the charge is more important than the size. So let's look at the charges. Calcium is +2, oxygen is -0, -2. Potassium is +1, bromine -1, potassium +1, chlorine -1, strontium +2, oxygen -2. So is everyone okay with those charges there? And I'm getting that from the periodic table because calcium and strontium are here as alkali earths being +2, oxygen and chlorine here as in -2 and -1. Is everyone okay with that? Okay. So we have these ones here. So that means that potassium bromide and potassium chloride are going to be one side smaller, so it's going to be less than, and then we're going to have strontium oxide and calcium oxide over there. So potassium is the same, oxygen is the same for the other two, so we have to choose between bromine and chlorine. So bromine is bigger than Cl, so since Br is bigger than Cl, we organize it as such. So the biggest ion is going to have the lowest lattice energy, and the smaller one is going to have the greater lattice energy. So in bromine, chlorine is already circled here, bromine is down there. So periodic trend, chlorine is above bromine, so it's smaller, or bromine is below chlorine, so it's bigger. So that one's there as on the far left. Then looking between strontium and calcium. The bigger ion is strontium because it's further to the left. So we have the bigger one is going to be, the bigger one is lower energy than the smaller one. So that's then the order from lowest to highest. So recap with this one. It has to do, you have to look between the charge and the size. Charge is more important than the size. So that's why we put the +2, -2s on the right and the +1, -1s on the left. And then we look to the size of the different ions. And the bromide is bigger than the chloride, so bromide is lower energy. And strontium ion is bigger than the calcium ion, so it is lower energy in that one. So questions with the logic here? Okay. All right. Let's see if you're following. Which one of these has the highest lattice energy? There's a periodic table there. I guess you can't see the periodic table. I'll spare you some suspense.
Hey, my dad took all my dad's in the
Okay.
hospital.
Oh no, okay. Yeah. Okay, so how many think sodium chloride has the highest lattice energy? How many think vanadium 3 oxide? How many think tungsten carbide? All right, so half the class is going for tungsten carbide. That is the correct answer. So, and it's from the magnitude of the charges. Does everybody see that? So, questions with this? They make rings out of this stuff. Does anyone have a tungsten carbide ring? I don't have any, but no. They gotta be very careful with these. They are really sturdy. You cannot use the jaws of life to crack them. So, like if you say you get like you're working on your car and you get your hand caught in the car or something like that, the firefighters they're called the jaws of life. They're like the snips that can cut through anything. They can cut through anything except for that's one of the things they can't cut through. So, what if you get your hand stuck in the car? They will have to rip the car apart to get your hand free. For instance, they can't just come and snip the ring. So that's a danger of this, and it's really pretty. It's really shiny. It's like black and shiny, and it's really tough, so it doesn't scratch very easily. So I can see, and it's cheap. It's cheap too, but like I said, it's only use it if you know that you're not going to get stuck, because there's not really any way to get rid of it. I mean, is it like invincible? No, you can vaporize it with a laser. Okay, but they use this stuff on the inside of. Anyone heard of a tokamak before? It's a fusion generator. So we have two different types of fusion generator, three if you count thermonuclear weapons. But we have two different types of fusion generators, and that's what's on the inside of the tokamak. That's a donut-looking thing. Like you've seen Iron Man, it's kind of like a tokamak. But dangerous stuff. Very, very sturdy stuff. So we use some ionic compounds for drugs. So for instance, silver nitrate. So silver nitrate, this stuff, it can be rough on a Caucasian because it turns your skin brown. It'll turn anyone's skin brown, but silver nitrate will turn, I mean, it's a little bit more predominant on a Caucasian, of course. But this stuff, well, when I was a kid, my dad's a chemist, and we had a bucket of, well, not a bucket, a bottle of silver nitrate, and if I ever touched this stuff, my hands would turn brown. And it would take a long time for it to go away. So that's one thing with silver nitrate. But it's a really good antimicrobial agent. So silver in general. So silver metal, salts of silver, they're very antimicrobial. And there's, geez, what was that? There's a show that talked about it. I think it was CSI or something. Anyways, the cure of it was colloidal silver. And maybe it was one of the doctor shows. But some people drink silver, like colloidal silver, and it kills bacteria. In fact, there's one guy, he looks like Papa Smurf. Let's see if we can ask Siri that. Can I see the blue guy that drank a lot of colloidal silver? Oh, geez. Whoa, that's way off. Man. Okay. All right. Let's look at. I'll show you the picture of this guy. There we go. There he is.
Whoa. Jeez.
So that's what happens when you take too much silver.
It's for real.
Not a Halloween costume. So, but silver nitrate though, they have Band-Aids with this. So you see Band-Aids with silver, and it has silver nitrate in it, and that kills, it's antibacterial. They also, so it's not just silver nitrate, like I said, silver metal does it too. They are experimenting with having underwear that has silver fiber in it, looking to use it for astronauts and special forces. So because if they have to go somewhere for a long time and like a deployment or space mission, and laundry facilities are not as accessible, for those type of things. So that's one way that they can have self-cleaning underwear. And this works for all that family too, copper, silver, and gold. So copper metal, I don't know why we don't make copper metal doorknobs. Well, probably because it tarnishes. But they would be self-cleaning. So they're antimicrobial, so that if you have copper doorknobs, they would disinfect themselves. So you wouldn't have to worry about it. Silver would work too, but silver is more expensive. And gold would work too, but gold's even more expensive. So, or you could have a silver sink. I remember seeing a place, I was house hunting, so it was way out my price range, but there was a silver sink there and never had to clean the sink. That's also why we have silverware, right? Those can also self-clean that way. Okay, so also barium sulfates. I've drank this stuff before for a CT scan. Stuff tastes terrible, by the way. They can use it as a contrast, mostly for GI tract. So you can drink the stuff, and then it goes to your system, and then you can take either an X-ray or a CT scan. CT scan is a bunch of X-rays. So if you ever had a CT scan, it's like this big donut. There's this big donut, and they stick you on a cart or on a thing, and you go in and you go out, and they have a little machine tells you to hold your breath, and then they take a bunch of X-rays, and it's over in like 2 minutes. So it's super fast. MRIs take a long time, half an hour, depending on full body MRI might take longer. But MRIs are totally safe, but I hate them. I've only had 2 in my life. One for my neck, one for my back. Neck after a car accident. But like, I'd rather have a CT scan. Am I getting old talking about all the medical procedures I've had done? But barium sulfate, use that for that. You have iodine in there? No, you don't. Okay, so you can use. They injected me with iodine. I had an iodine drip, and the iodine can tell you where your blood vessels are. So the barium sulfate can tell you where your intestines are in like your stomach from an X-ray, and you can add the iodine into your blood, and it tells you where your blood vessels are with the iodine. There's a contrasting agent also for MRIs. I don't remember what it is off the top of my head, but you can image blood vessels with that too. Okay, so calcium sulfates. This is how you make plaster casts. Has anyone ever used these to make sculptures before? To make an investment for a sculpture? That's fun. So it's too bad they don't have this class here. I took this class at UH Manoa. I get free classes. I get 6 classes free per term. And I took bronze sculpting. That was such a fun class. And it's dangerous. It's a super dangerous class. There was, because you have molten bronze, right? You have molten bronze, but where you're doing something called the lost wax method. And the way that you do this is you make a wax sculpture of what you want, and then you use another type of wax to make this irrigation channel. I forget what it's called. Anyways, because it's a red wax, and sculpting wax is kind of brown. Anyways, you make the wax sculpture what you want. You make this irrigation channel, and you put this into a plaster cast. So you take plaster, and plaster is calcium sulfate. And when you mix it with water, it forms calcium sulfate, I think 9 hydrate. It makes a hydrate. It's exothermic. So when you mix it together, it gets hot. And then it gets hot, and then you take that and you wrap your sculpture. You put chicken wire around it, and you pour the plaster into that, and then you bake it into a kiln. Now you let it sit for a bit, and then you typically flip it upside down. You bake it into a kiln, and it hardens the plaster, and then all the wax drops out. And you take that, and then the bottom is sealed. You flip it back upside down, right side up, and you pour molten bronze into it. And then the molten bronze goes to all the spots that you had where the wax, it was the lost wax. Then you have the bronze sculpture, and you break up the investment. It's kind of fun to get a sledgehammer and an axe, because you have to use the axe to cut through the chicken wire and then blast it apart with some sledgehammers. Then you have to cut the irrigation channel off of it, and then you have your plaster. You have your bronze sculpture. So a lot of fun. But calcium sulfate used for that. We tend not to use that for plaster casts anymore. We usually use fiberglass for that, or nothing, or we use a brace. I mean, the cast now, it's rare that you would see a plaster cast unless you go to an undeveloped country and you break your arm. Now, if we're going to immobilize something, usually either fiberglass or have some sort of plastic, like, or not even plastic. I sprained my ankle one time, and they gave me it's a really awesome brace. It's made of nylon, and it had a bunch of Velcro, and you can wrap things up, and I could walk again after having that thing on. I was on crutches, and it was magic. I could walk again. But a lot of times when people break their arms now, you have like a plastic sheet, and they can just they can strap their arm or something like that into the plastic cast. So our casts are much better now. Has anyone ever had a fiberglass class before? I have. The itching is just horrible. It's like, don't think about it. You know. So at least then now you can take it off and itch. So, but plaster, we still use this for art too. So, like I mentioned with the lost wax method. Potassium permanganate. So this is used, it's an antimicrobial as well. Tends to be very effective on fungi. Used to treat trench foot. So this is trench foot is just when you have a really bad fungal infection in your foot. And that's the go-to treatment for that. Has anyone ever seen the show Naked and Afraid before? That like you can bring two things from the real world. One person one time chose potassium permanganate. So that's what she chose, and it was to purify water and to treat infections kind of stuff. So I like the fire start and the machete. That's what I would pick, myself. But heck, go in the chemistry route. Why not? So potassium iodide. So antiseptic disinfectant, and it's also used to prevent radiation sickness. And this is a specific kind of radiation sickness. So I'm not too worried about it now. Actually, did you guys? I'm sure you were here for the nuclear scare last year. Oh, that was pretty scary for me. But what we do, we have potassium iodide stockpiled. We have this as part of our nuclear defense, although we as Americans may not need it. So Chernobyl, if you heard of Chernobyl, this is 1986. There was a nuclear power plant that melted down and exploded. Not a nuclear detonation, but just a regular explosion, kind of like Fukushima is a regular explosion, chemical explosion. And then radiation was released in the atmosphere. So here, we're in the United States, and we eat lots and lots of enriched foods. So you will not likely see any goiter. That's when you have an enlarged thyroid gland from lack of iodine. So we put iodine in our salt. And anytime you eat processed food, you're eating iodized salt. And we also jam-pack B vitamins and everything. So it's very rare to see an American with a B vitamin deficiency. So we jam-pack all these things. And those of us that don't eat processed food, so we do have some salt. So kosher salt has no iodine in it. But if you eat fish from the ocean, you get iodine. So, and that's believed to be some of the dietary laws for religion. So like in Christianity, there is a ritual that you should eat fish on Fridays. It used to be every Friday, and then now it's just changed to Lent for Catholicism. But the idea was for that was iodine. It was that if people ate fish once a week, they would get enough iodine in their diet. So that's a hypothesis, though. So, but what the potassium iodide does is your thyroid. It produces a hormone called thyroxine, which regulates your metabolism. It's your idle. Like when you turn your car and you have an idle in your car, your metabolism is kind of like the idle on a car, but for a biological being. And more thyroxine, that means you're higher your idle. And some people actually in the past would add more. So they add more thyroxine, and that would create a condition called hyperthyroidism, where your thyroid was producing too much thyroxine. And why would you do that? You lose weight. Higher idle, you burn more gasoline, you burn more calories, lose weight. So it has been suggested that Kenny in South Park, are you familiar with South Park? Kenny in South Park might be hyperthyroid because he's always cold. So if he's hyperthyroid, he would burn off all of his body fat, and that's why he's always bundled up so tightly, because also in Colorado it's always snowy there. So he was cold and had no body fat, so he was always really, really bundled up. But like I said, it affects our thyroid, and if one of the byproducts of a nuclear detonation, nuclear reaction is iodine-131, which is radioactive. Whenever your body gets iodine, it rushes it to your thyroid. So, like I said, it wouldn't affect us too much in the United States because we enrich our food. And under communist Russia, they had a much poorer diet, so they didn't have iodine in their food. And then the iodine from the nuclear reaction went in, and it gave a lot of those people cancer and gave them a lot of thyroid issues. It can also, so if there is ever a nuclear event and someone hands you a pill and says, take this, you should take the pill. You shouldn't just go ahead and take them anyways. Like, oh, I'll just eat lots of iodine just in case, I get, in case North Korea wants to, try again. Or, they didn't try the first time, but, the reason for that is you can create a condition called iodism. Too much iodine causes iodism, which is also bad. It's the old moderation. Too little is bad, too much is bad, right in the middle is good. And we do sometimes purposely irradiate the heck out of our thyroid. That's to treat certain things like Hashimoto's or Graves' disease. That's when you have an autoimmune disorder where your thyroid is being attacked by your body. And that also causes hyperthyroidism. There's also hypothyroidism, which means your thyroid is putting out too little thyroxine. And that's also, the effect of that is obesity. So some people that are hypothyroid have problems with obesity. Hyperthyroidism, it's also a psychological issue. So people tend to be very upset. Their mental health goes down. Well, for both, more so for hyperthyroidism. So, and if anyone has known anyone that has to go through that, it's a pretty rough diet. So if you're going to be irradiate your thyroid with iodine-131, you have to go on a special diet before you take it. Otherwise, it doesn't have PEEP. because our food's too enriched. So basically, you can eat meat and fruit. That's the only things that really don't have iodine in them. So if you eat anything processed, milk has iodine in it because they clean the lines with iodine. So iodine can be used as a disinfectant, also written there as a disinfectant. So we do that for our dairy equipment. So that means any cheese, no milk, nothing that they put salt in, no processed food. So no lean cuisines, no flour, nothing like that. It's all super enriched with iodine. So meat and fruit, that's all you can eat. And then after a while, you'll deplete all your iodine in your body, and they zap you with iodine 131. And then it has a half-life of 8 days, and then it puts a huge amount of radiation in your thyroid, and it essentially kills it. And then you go on hormone replacement therapy. That's how they treat the Graves and Hashimoto's, is you irradiate the heck out of thyroid and then go on hormone replacement therapy. You can just take pills and then live a long and happy life. Lithium carbonate used to be used to treat manic depressive disorder, specifically bipolar. I guess manic depressive is a part of bipolar. Every time I talk to people in the chem lab, I start to feel old. Is Nirvana too old for you guys? No, Nirvana's still cool. Well, not cool, but it's not unknown. So there was a song called Lithium from Nirvana, and specifically treatment. And this was one of the first treatments for bipolar, was lithium carbonate. So it tends to even out the mood of people. Magnesium sulfate. Hey, we use this in lab. So used to treat eclampsia during pregnancy. Also, in general, magnesium salts are also laxatives. So magnesium sulfate, Epsom salts, they're laxatives. So if you have stomach issues, you can take calcium. Is calcium carbonate? No, it's not on the list. Tums is calcium carbonate. That's an antacid. So problem with Tums is it can also cause constipation. Magnesium hydroxide, milk of magnesia, that is an antacid. It's also a laxative. So you can use it to treat any of them. Pepto-Bismol, that's bismuth subsilicate. It's neither. That coats your stomach. Also, bismuth subsilicate, it can turn your tongue brown. So if you eat Pepto-Bismol and your tongue turns brown, that's totally fine. I had a student freak out about that one time. So, oh, magnesium hydroxide, that's right there. Oh, geez. Milk of magnesia, also known as Rolaids. Sodium bicarbonate. Oral antacid, we don't use it anymore. I don't know why Tro wants to put that in there. We don't use that because of the sodium. So calcium carbonate is the most common. So at least the way that antacid works, there are 3 different types. There's a direct antacid, so that neutralize the acid in your stomach. There's also things called H2 blockers. So those are Pepsid AC and what is, it's not Xanax, Zantac. There it is. Zantac and Pepsid. They're known as H2 blockers. So you're probably familiar with H1 blocker. So Benadryl, Claritin, those are H1 blockers. Those deal with your histamine response. So meaning if I'm allergic to something, mold, I'm allergic to mold. If I breathe in mold, my body goes, oh, this is bad stuff. I'm going to release these chemicals called histamines, and then I'm going to have a reaction to that, which involves an immune system response, which means my eyes get watery and my nose gets stuffy. How do you prevent your eyes getting watery and your nose stuffy? If you take an H1 blocker like Claritin or Benadryl, that will be an H1 blocker. It'll stop it in the tracks. H2 blockers, Those similar to your histamine response, part of the immune system, but it works in your stomach, and then it could reduce the amount of stomach acid you produce. So the process for that is not very well understood. We kind of get it. This is known as a physiological black box. So it's too bad all my nursing majors aren't here. They'd all get excited when talking about this stuff. We don't know a lot what goes on in the body. I mean, we lose track of what's going on because like when we do things, we can study the molecules. When we strip them out of the body, we break them out of the cells. Do they work in a test tube the same way they work in the body? Maybe, maybe not. These pathways that we have H1, H2, are they real? We kind of figure it out by giving people drugs and seeing what happens, and we kind of put it together. But so if you study pharmacy, that's where a lot of stuff comes in. You have these pathways, and they learn about these pathways, and some drugs inhibit some pathways, some do other things, and some do. But again, it's like a lot of guesswork. So we're trying to figure it out. We got a decent understanding, but not. It's still, like I said, it's a lot of guesswork. That's why we can't just engineer a drug saying, "Ha, this will solve all your problems," because like we have to well, we do trials for a while because we don't really know what's going to happen. So maybe in the future. Okay, and then the last one type, I'm talking about antacids, the proton pump inhibitors. That's the last one. That's Prilosec and Nexium, those kind of drugs. Those work. The way that your stomach works is you take you form hydrochloric acid in your stomach. So it's HCl in your stomach, and along your stomach walls, they rip a hydrogen ion off of water and they transport it through your stomach lining to your stomach. And that action is called a proton pump. The Prilosec or Nexium, those proton pumps inhibitors, those stop that action. And it can pretty much more or less turn your stomach off. I found out that I'm the lucky 1% that can't take proton pump inhibitors because one thing in your stomach, it produces most of your serotonin. So your serotonin is a happy chemical. So like you eat Halloween candy and you get happy because your stomach releases serotonin. It's a good thing. Your body is rewarding you for eating good food, like chocolate, good food, right? Or donuts from Krispy Kreme. That's like happiness in a ring, kind of thing. So, I mean, you can also get serotonin in your brain, of course. But most of it's made in your stomach. And I'm the lucky 1% that can't take it because it shuts down all my serotonin production. So anyways, that's all antacid stuff. So there's other drugs other than sodium bicarbonate. I personally use it as a toothpaste. So I take sodium fluoride and then I put sodium bicarbonate on it and I brush my teeth with it. And I do that actually because I'm trying to change the microbiome of my mouth. My dentist recommended I do this, and I've been doing it for a couple of years, and now I get A+ on my oral hygiene whenever I go to the dentist. So maybe it works for different people. I don't know, but so sodium bicarbonate can be used with that. It's alkaline. It's basic. So and the dentists suggest. Still working on it. And we're doing studies on microbiomes. We're doing studies here, actually. Professor Sally Irwin does studies with microbiome. So, and seeing what the microbiome does for people. And this is new and upcoming medicine. So looking at people not just as their individuals, but also looking at their microbiome. And also looking at what type of germs people are exposed to, because some germs are good, some germs are bad. And people that live in very sterile environments often also get autoimmune disorders. So when you're younger, being around germs is not necessarily a bad thing. So sterilizing everything all the time can lead to health problems down the road. So I still throw a lot of bleach on stuff, though. But it depends on what I'm doing, though. I wash my hands before I eat lunch. That's for sure. So doesn't mean that if germs are good, oh, give me more, I'm going to go, shake everyone's hand and then, put my fingers in my mouth. That's not a good idea. But, sleeping with your dog or your cat, that's probably okay. But sodium bicarbonate, this is also can be used to treat acidosis. So there is your acidosis is when your blood becomes acidic, and there is alkalosis. So your blood can be too alkaline. Anybody want to guess what the most common cure for alkalosis is? Hold your breath. Because when we'll learn about this next semester, but our body uses sodium bicarbonate and carbonic acid as a buffer, which means our blood pH has to be about 7.4. If it's not 7.4, bad things can start to happen. And so what I mean by bad things can happen, proteins can denature. They change shape, and when they change shape, they don't work as well. And patients that have issues with their lungs or kidneys, especially, can be prone to acidosis and alkalosis. And if the blood pH changes, then the organs, so the proteins start to denature, then organs start to shut down, start to shut down, patients crash, they die. And death can happen quickly. So this can be scary with acidosis. And I was fortunate to get acidosis once. That was not very much fun. It was, it was 10 years ago when the volcano started erupting. I was at a conference at KMC, Kilauea Military Camp, and we were at level purple. I guess there's different grades. Black is like severe threat to everybody, get the heck out of there. And I think green or yellow is like okay, and orange is like uncomfortable to most. And then I was at purple, which is uncomfortable to everybody but not lethal for most. And they kept us there, and after breathing the stuff for 3 or 4 days, I got acidosis in my blood. So it did not feel good. I mean, obviously I survived, but I wasn't acidic enough that they injected me with sodium bicarbonate. My kidneys worked fine. I just had to drink a lot of fluids, because I mentioned your lungs. So because I remember this because one of the things I started to hyperventilate. That's one way that you can lower your blood's, raise your blood's pH is hyperventilation. That stuff, you're letting out carbon dioxide. And with letting out carbon dioxide, your carbonic acid, H2CO3 level, your blood goes down. So your acid level goes down, your pH goes up. So more basic means higher pH. So that's one way your body will try to fight acidosis, is by hyperventilation. And it hurts, by the way. So, and also, what do you do to treat somebody who's hyperventilating? Give them something to breathe into, because then you reabsorb the CO2. So to prevent that. But like I said, severe cases, sodium bicarbonate. I remember I met this one guy. I do feel, since I'm a community college professor, I feel a drawing in the community, and when I'll talk to people that have science questions that are not my students. And this one person, he asked me, he says, I like taking a spoonful of organic baking soda every day, and I do that to treat gout. And he says it's great. My urine is alkaline now, and I love the taste of the sodium bicarbonate. It's sweet and it's purple. I mean, first of all, organic means carbon containing. There is no such thing as organic sodium bicarbonate. So no such thing as organic baking soda. This is, by definition, inorganic. So then he's like, what do you think of my idea? I was like, I felt bad telling him, I was like, to be honest with you, if you have to take baking soda to control your acid levels, you should get your lungs x-rayed and your kidneys checked, because there's probably more likely a problem there. And if you're also urinating alkaline, that's probably a very bad thing too. Urine is supposed to be acidic. So again, I'm not a medical doctor, so if those are conditions you have, you should go see your primary medical doctor, especially everyone listening online. I'm not advocating this as an MD, but it's something you should get checked out with your primary if you have that issue. So, anyways, now sodium fluoride. Sodium fluoride used to strengthen teeth. This is especially important when you're younger. So Hawaii, we do not fluorinate our water here, except on military bases. So the municipal water does not have fluorine in it. Most other places do. And what fluoride does, your teeth, your tooth enamel is a mineral called hydroxyapatite, and it's calcium, phosphorus. It's calcium phosphate and hydroxide. I forget the ratios. But what fluoride does is it replaces the hydroxide in hydroxyapatite. It makes it less soluble, and it makes it harder. So it does two things, and fluoride is also antimicrobial. So so I guess it's three things, three actions. And I mean, you can still use it as an adult. So we can remineralize our teeth. It's not like our teeth, we slowly erode our teeth until we die. We actually can remineralize our teeth, and we do it with our saliva. So our saliva has the ability to grow tooth enamel on our teeth. And so tartar, so plaque. Now plaque in your teeth is different than plaque in your blood vessels. Your blood vessels is kind of it's typically cholesterol and other lipoproteins in your circulatory system. We use the same word, but plaque in your teeth is it's undigested food and sugars and bacteria. If you have lots of plaque on your teeth, your saliva can try to remineralize that, and it forms tartar. Tartar is hydroxyapatite, but in a spongy sort of structure. That's why they can scrape it off with their dental instruments. So, but like I said, our teeth will remineralize over time. So even as adults, sodium fluoride is still beneficial, but you don't need much. Just a pea-sized. And a pea, like half a centimeter size thing. So that's all you need on your brush your teeth twice a day. Not like they do in the commercials where they dump a bunch of stuff. That's a marketing ploy, by the way. When they have commercials and they have how-tos and they always oh, shampoo, and they have a handful of shampoo in their hair. You don't need that much shampoo. You don't need toothpaste. You don't need to put the whole. They show a picture of a big swath of it. You just need a little tiny bit. That's all you need. So for kids, though, if you have a child here, you're growing up here, you could even give oral sodium fluoride or tin fluoride, stenic fluoride to children because when their teeth are being formed, they'll form it with the fluoride on it. Again, it's also an issue of moderation. Too much fluoride can cause damage to your bones because in your stomach you can form hydrofluoric acid, which dissolves your bones. So it's happy medium. A little bit's okay, too much is dangerous, and none. This is one of those highly debatable things. Many people don't like it. Hawaii has one of the highest rates of cavities, and it's because of people that have grown up here without the sodium fluoride in their water, and if they don't brush their teeth every day. Lots of people don't brush their teeth every day. You can get your teeth to form without the fluoride in them, and they will be weaker than someone who does. And this was also discovered naturally. This happened in Colorado. There was some water that people drank that has really high in fluoride, and the dentists wondered, there are no cavities with these people. What's going on? And it turned out it was a fluoride. So. Also, besides sodium fluoride, you can have tin fluoride. So Crest Pro Health, if you're familiar with that, Crest Pro Health uses tin fluoride. The difference between sodium fluoride and tin fluoride is that the tin fluoride tends to dry out your gums a little bit more. So I personally prefer sodium fluoride. That was also off a recommendation from my dentist as well. So I'm kind of mirroring his, which made sense. So use that to strengthen teeth. And I hope I don't get any hate mail about this, because this is always, some people feel very passionately about this topic. Zinc oxide, this can be used as a sunscreen. So zinc oxide and titanium dioxide are often used as sunscreens. So I have to wear a lot of sunscreen because I'm very fair. I use organic sunscreens, not in organic as in a hippie FDA work. I mean, it has carbon in it. So I buy the cheap jugs from Target, basically, the sport ones, SPF 30 or SPF 50. And SPF is another thing that's kind of not as well understood. SPF is 1 over, so the difference between SPF 30 and SPF 50 is about 1.5%. So it's 1 over 30 and 1 over 50. So 1 over 30 is about, I mean, close to 3%, and 1 over 50 is 2%. So you're looking at a 1 or 2% difference. So like I remember when I was a kid, we had SPF 8 was like, whoa, that's a lot. It's 1/8. It's blocks 87.5% of the UVB radiation. So zinc oxide, I don't like this as much because it clogs my pores. So I see surfers like this stuff quite a bit. It's a really strong sunscreen. I mean, it's also safe for the reef too, which is good. I don't surf, but I don't like it, like I said, just because it clogs my pores and then it makes me look kind of ghostly white. I'm already white enough as is. And also titanium dioxide, like I said, with that, for very dark complexion people, titanium dioxide can make people look blue. So blue, maybe even purple colored. So that's one thing about the other ones. It wouldn't work on me because, like I said, I'm too fair-skinned. But I'm all about sunscreen, but that's because I get sunburned. But I know another contentious thing because of the damage to the reef. But okay. How are we doing? Anybody have any questions with my Chemistry and Society lecture on organic compounds and their uses? All right. So maybe if you've had chemistry in high school, you've probably seen this before. And I mentioned it briefly last class. These are known as Lewis dot structures. Now, remember, electrons are not dots. They're this kind of fuzzy area of uncertainty. But fluorine has 7 valence, 7 outer. Electrons has 2 core. The core are not listed. Likewise, oxygen has 6, nitrogen has 5. And we group them as such. And fluorine can meet another fluorine atom. And what they do is they share 2 electrons. And the magic number for many things for bonding and electrons is 8. So it's just low energy. So I will tell you the secret to chemical bonding. The reason why things bond, whether it be ionic, metallic, or covalent, is because when groups of atoms come together, they can share electrons in some fashion, and the manner in which they share the electrons is if it's lower energy than either them holding the electrons. If it's lower energy, then it'll happen. So that is the whole idea behind bonding. That the most stable is the lowest energy electron configuration between the groups of atoms, how it's shared or not shared. And you can do that using quantum mechanics, and there are molecules that form that do not follow the octet rule. But in general, though, in this class, we base most things off of the octet rule, meaning things tend to bond to be like noble gases. And noble gases are not reactive because they already have the most stable chemical electronic configuration, which is true. This is true. You'll see other configurations in transition metals, for instance, and we'll also talk about octet rules expansions. You can have less octet rule, so the boron and aluminum will bond. So aluminum is a metal; it can still covalently bond. Can form compounds that break the octet rule. And also, you can get things in period 3 and above that will break the octet rule. But, and generally speaking, things like to be like noble gas configurations, which means 8 valence electrons. So that's where the octet rule came from. Okay, so fluorine has 7, The other fluorine has 7. So 2 fluorines get together, and you're like, you know what? What if I kept 6 electrons, you kept 6 electrons, and we just shared these 2? That way, can I darken this? That way, I have 8. You have 8. And we're both happy. Now we both have 8 electrons, and we have a very beneficial relationship. So that's the idea behind the covalent bonding there. They share the 2 electrons, and in this case, the same atom, they share it equally. And instead of drawing it this way, we typically draw a dash. And that dash, the line implies 2 electrons shared between the atoms. And oxygen, the same way. Oxygen has 6. So how do 2 oxygens, each with 6 valence electrons? Well, they keep 4 to themselves, and they share 4. And so now this oxygen, that one on the right has 8. This one on the left has 8. For the students online, I'm just covering one of the oxygens with my hand. And we denote the 4 shared electrons as the 2 lines. And then nitrogen has 5 valence electrons. It can keep 2 and share 3. So 6 electrons are shared between the 2 atoms and denoted by the triple bond, the 3 lines. And we can actually get quadruple bonds. So you can get as high as 8 electrons shared between 2 atoms. And that happens for ruthenium. So it can form an extra pair. But that's above and beyond this class. If you're wondering if there's anything bigger than a triple bond, yes, there's a quadruple bond as well. Okay, so we're at time. I mentioned this when we talk about periodic trends. This is the concept of electronegativity. And I've always wanted to go to Lahaina for Halloween. I'm not going to make it this year, but maybe next year. But if you go somewhere like that, have you ever noticed if you go to Halloween or some other festival, if you see a really attractive person there, there's like a ring of people that forms around that person. They have the canny ability to draw others to themselves. That is like an attractive person can draw others to them. Like, has anyone ever seen celebrities before? Like, I saw Eddie Murphy. That guy was super handsome. Wow. You know, he was. I went to a taping of the David Letterman show, and there was another female celebrity, and she was beautiful. I mean, it's just, I can see why people are like, wow, celebrities in your Star Trek. I mean, they are very good looking. You know, not surprising. You know, and so if there's ever celebrities out and about, usually people are flocked to them. They're drawn towards people. Well, just like an attractive celebrity drawing people to them, atoms can draw electron density to themselves. And there's a periodic trend. The trend is to the right is increasing and up is increasing in the periodic table. And the most electronegative atom is fluorine. And you think it's helium, but the noble gases do not have, we do not include them in electronegativity because they tend not to bond as much. So we'll learn later that the noble gases do, in fact, react. They used to be called inert gases. But then after we find out they react, we're like, all right, we'll call them noble instead. Noble is unreactive. So fluorine is the most electronegative atom. And this is, what's listed here, it's not written in the textbook. It's called Pauline's electronegativity. There's different types of electronegativity, depending on who describes it. Pauline's electronegativity is the one that's used most frequently. And quite frankly, it's the only one that I know for any type of usage. So, and we'll talk more about this in the future for the effect of the electronegativity effects on bonding. And it's not, I mentioned above, up being high, and to the right being high, but you notice that there's a kind of an island there. You have some compounds there. Those can form covalent bonds, but they don't act like nonmetals. They act like metals. So I mean, gold is clearly a metal, and carbon and nitrogen is clearly a nonmetal. So it's not like, and you can see gold is got almost the same electronegativity as carbon. It's even higher than phosphorus, but phosphorus is definitely a nonmetal, and gold is definitely a metal. So, but anyways, why do I care about electronegativity? Well, if you have a molecule here, like hydrochloric acid, or I should say hydrogen chloride. Well, I guess I should back up. When we had like fluorine and oxygen and nitrogen, all the same atoms, they share their electrons completely evenly. This is a 50-50 split. So that means if I'm a fluorine atom and I have my twin brother here and we want to share electron density, I get exactly 50% of the electron density, and my evil twin brother will get the other 50%. I don't have a twin brother. But now if you have two different atoms, any two different atoms has a difference in electronegativity, and as such, so here with hydrogen and chlorine is more electronegative than hydrogen. Why is that? Well, chlorine has a +7 center, hydrogen has a +1 center. The electron density gets drawn towards the chlorine, and I said density, it kind of flows. It doesn't even necessarily flow. Electrons can be in many different places at once, and the electron just spends more of its existence in the chlorine, close to chlorine, and less of its existence in hydrogen. But it's there both at the same time. And this has also been described as being kind of like a blanket hog. Like, have you ever shared a bed with someone and then that person has taken all the blankets away from you, kind of thing? That, or maybe you're the blanket hog and you leave your bed mate without any blankets. Kind of like this. It has hydrogen and chlorine, and here's chlorine taking all of the blankets away from hydrogen. Hydrogen's shivering, it's cold. Chlorine's all warm and snuggly. But instead of blankets, it's electron density. And instead of shivering, hydrogen has a slightly positive charge. Chlorine has a slightly negative. So that delta, that's lowercase delta, that means partial. So same thing in math. The delta is partial differentiation. So partial positive, partial negative. What do I mean by partial positive? I mean less than positive 1.6 times 10 to the minus 19 coulombs. That's the charge of a proton. What's partial negative? It's less than negative 1.6 times 10 to the minus 19 coulombs. That's the charge of an electron. So it's less than that. And then you have what you call a polar covalent bond. So polar because there's a positive end and a negative end. Just like, although this is magnetic, the Earth has a magnetic field. Our positive end is our North Pole, where the polar bears are. Our negative end is the South Pole, where the penguins are, kind of thing. So it's magnetic. It's not electronic, but it's electronic for atoms, and they have a positive and negative end. And this is something I have to teach, but I don't like teaching it. I disagree with it. Let the record show that I disagree with this statement. But the effect of electronegativity on bond type. So for a small difference in electronegativity, this is said to be covalent. Intermediate is polar covalent. Large is ionic. So where this comes into play, where this is important, is organic chemistry. If you take organic chemistry, what they'll tell you is that the hydrogen-carbon bond is covalent. And I can tell you that it's not. So if you have two different atoms, it's a polar covalent bond. If you have the same atom, it's a covalent bond. And there's a logical fallacy with the organic chemistry saying that it's a covalent bond because oxidation, so removal electrons, can be seen as removing hydrogen. And hydrogen, they say it's because hydrogen is electron rich. It's because hydrogen donates electron density into the molecule. So they'll say, oh, it's covalent but then they'll come back and say, well, maybe not. So depends on who you ask. Organic, this is because, like I said, organic chemistry. But when we talk about bond polarity, especially for polar molecules, an easy way to remember it is if it's two different atoms, it's a polar covalent bond. So just do that. It'll make your life much easier. In ionic, and this is actually kind of a fuzzy thing because you can get covalently bonded atoms that break this. There's several covalently bonded molecules where the electronegativity difference is greater than 2 in the Pauling electronegativity scale. So am I done for all right, there's my shut up alarm is going to go off now, and it's going off. So I will stop here, and I will see you on Wednesday on a spooky Halloween.